let's look at something else. Here's one, just to keep your trig skills up, brushed up. Let's go ahead and look at this. Again, we're sticking with the American system of measurement. 25-pound cart, stationary at time 0, and thereafter subjected to a sinusoidal loading up the ramp. Up the ramp. And then they give us some prescribed value in part A for the vertical shift on that sinusoid of 5 pounds. Determine the velocity of the cart at 1.5 seconds. And then part B, find the value of B, the vertical shift necessary, for which the velocity of the cart would be 0 after the first complete cycle of force application. So it's the sinusoid has an amplitude of 10 pounds, vertically shifted by an amount B. Do they give us a time, a frequency on this function? Yes, it's built in right up there, right? Sine of 6t. Okay. So this is problem 209. So we have a 25-pound cart. We have a normal. The incline is at 20 degrees. Oh, one thing on your papers, if you get in the habit right at this point in college of putting a little circle up there to indicate degree measure, because you're going to be jumping between degree and radian measure frequently. And sometimes you will be dealing with 20 radians, numbers like that. So if you just get in the habit of putting the degree symbol there, then you will know that you need to be, for any calculations, need to be in that mode with your calculator. It'll just lessen errors on your part. And so then this ramp is at 20 degrees. And I don't believe there's any friction. And we have this loading function then, capital F, which is described as being the sinusoid, which happens to be 10 sine of 6t plus b, which is your vertical shift. The graph of that loading then looks like something like this. And then in part A, they want this B value to be 5 pounds, didn't they? 5 pounds, and the amplitude of the function is 10 pounds. So if I imagine my scaling here to allow for this to be the 5, thinking of this as 5, then doubling that is going to be my amplitude. So this thing's going to come up pretty high, and it's actually going to sweep down to a -5 low point in its range. And look like that over time. Feel good? And the period of this function is going to be whatever it takes for 6t to finish a sinusoidal cycle. The entire argument of the trig function taking on that angle, taking on a value of 2 pi, which you know is where a sinusoid would finish a cycle. So then we set 6t equal to 2 pi, and you end up getting, it looks like pi over 3, seconds is the period. So just a touch more than 1 second of time. Right? Okay. Now, this thing started at rest, didn't it? At rest. Okay, initially at rest. Somebody who doesn't speak up too often, tell me what's going to happen initially. Here's the loading. What's going to happen initially? This thing's sitting on a frictionless ramp. Somebody who doesn't speak up too much. The silent majority.
Initially, it's going to go down the ramp.
Initially, why do you think that, Heather?
Because the force is not yet large enough to.
Yeah.
It's starting at the.
Okay, because you can see that there is a component of this loading due to the weight that's actually down the ramp. Now that has to play into this. I mean, when you start thinking impulse, it's not just some loading function that's given to you, it's all the forces that create an effect on there. So there is a constant force of 25 sine of 20 down that ramp, right? 25 sine 20, so that's exactly right. So this thing, because of this, and the fact that this initial pulling up the ramp isn't enough to overcome that, this thing's actually going to start moving down the ramp first until there's enough zip in this loading to cause that thing to first of all overcome this, and then there has to be a net unbalanced force up the ramp to cause this thing to then slide down and come to rest, and then hopefully there's enough there to get it going back up the ramp actually. Make sense? Okay. Now let's go back over to the other board for just a second and think about that problem we looked at earlier. Here we had an effective impulse created by the sum of these loadings, the friction force and the P force. And then we showed a superposition or an addition of those two functions to create the net impulse. So rather than just cranking out, now we can come back over here, rather than just cranking out the mathematics on this, what could we do to adjust this diagram so that our diagram will show us graphically the active impulse?
Constant force.
Okay, what's 25 sine of 20 degrees? Make sure you're in degree mode. 25 sine of 20 degrees. Okay. 8.55? Good. Okay. So that's 8.55 pounds down the ramp. So we're going to have, let's see, if I call the direction up the ramp positive x, then we have our net force, or in other words, our sum of forces acting in the x direction is going to be equal to our F loading due to the sinusoid minus 8.55, which is that sine component of 25 pounds. So we would do what to this picture? We would take that graph and shift it down by the amount 8.55. Okay? So the effective impulse then, if I'm now drawing this sum of forces over time, I'm going to bring this sinusoidal axis down from B. I'm going to bring it down by 8.55, aren't I? Okay. So it's actually, thinking of that as the 5 originally, it's actually going to bring it down and make that the nodal axis of that sinusoid negative. So this axis is sitting down here at b minus 8.55 in value.
B equals -3.55 because you had a 5 upward shift. If you have to shift it down from your original 8.55, it was shifted up 5.
Well, here's the original impulse. This is the F impulse up the ramp.
Right.
And so what we're doing is we're taking away from that, aren't we? By this amount. So we're just going to bring this down. We're just going to take 8.5 off of that. So that'd leave this down at minus 3.55, wouldn't it? Where the node axis would be?
Yeah.
Is that okay?
If B is 5, then because most of the sinusoid is below that axis, that means most of the force is directed back down along our path. We're just going to slow this line back.
Well, it depends on how far we let time go on that cycling, right? So this thing is going to arc up.
I think what he was talking about is you have negative 8.55 written.
Yeah, no, I understand that you're talking about
Oh.
the situation.
Oh, B minus that.
There's the Thompson.
B minus that is the negative 3.55, which I believe is where it should be,
Yeah, it is.
right?
I thought you were just labeling it negative 8.55.
Yeah. Well, I screw up frequently, so I'm glad you guys are questioning it. Okay. But I think we're okay, aren't we? Okay. And so then this thing is doing this. I'm trying to give you a good visual understanding of this concept. That's what's important. So then, look at what we've got. See this little bit right here? You see that? That little tiny shaded spot? That's a negative impulse. That's actually causing the thing to do what? Physically? Accelerate down the ramp, right? And there's a point in time right here, isn't there? Isn't there a point of time right here? What's happening to the object right at that instant?
It's not accelerating. It stops.
No, it hasn't stopped.
It's not moving, there's no acceleration.
It's moving, but the acceleration at that point is 0. The forces are balanced. The active forces are balanced at that instant. So that means there's no acceleration at that instant. And then, once you get past that point in time and over to this spot, what's this doing to it?
Accelerating up.
Yeah, this is force acting over time that's actually imparting a force up the ramp over time, giving it an impulse up the ramp. Does that mean it stops it?
No.
Not necessarily. Well, when's it going to stop?
When the area is equal to the tiny impulse underneath.
Yeah, good. I'm not going to put colored marker up here because it's hard to erase. But do you see that little area right there? When we get a symmetric portion right there, I'm just going to hold the marker there. When we get a little symmetric portion there that's equal to this, because see, the thing originally started at rest. There was enough impulse here, this little part here, to cause it to accelerate down the ramp. Here now the acceleration is 0. And then if you go symmetrically on the other side of that, on this sinusoid, that same amount of area is going to then bring it back to rest again. Isn't that interesting? So then this portion right here is going to cause it to be actually physically moving back up the ramp. The portion from my 2 fingers, between the marker and my finger, that impulse truncated off right here, cut off right there. These markers are not good. Everybody with me on that? So it's from this point on, right there, it causes it to move up the ramp. Okay, good. Now, I forgot what we're supposed to solve for. What are we doing?
Determine the velocity of the cut at t equals 1.5 seconds.
Okay, at t equals 1.5 seconds. Well, look at this. Our period of this function is just a touch over 1 second. So we've got to we need to carry this impulse function out further, because this is our, the period right here is the pi over 3 seconds. So we actually have to carry this thing further until we get to somewhere wherever 1.5 seconds is. So we need to get this thing out here to wherever 1.5 is. Now I'm not sure, let's see, what's a quarter of the period? Because on sinusoids, a quarter of the period are always nice to keep tabs on. Pi over 12. The reason is because that's the distinction between our crest, nodes, and troughs, right? When you break up a sinusoid. So quarter cycles on a sinusoid is useful. So pi over 12 is roughly a quarter. So it's roughly a quarter of a second through these locations. Here to there to there is roughly a quarter second. So we're going to be going, we need to get out to 1.5 seconds. So it's going to be right near, it's going to be right up here near a crest, isn't it? Okay. Could you solve this impulse the impulse portion graphically?
If you were determined. If you were determined.
If we were determined, we could find this point in time where this trig function shifted down, zeroes out, and then we could move symmetrically past that and then start our impulse here and then carry it on through till we get to the 1.5, and we could do it graphically. But it might be a little tedious. So let's go back now and rely on the mathematics. Which I think we'll probably find easier. So we defined up the ramp as positive. So what we're trying to work up is this effective force over time is equal to the change in momentum. And they wanted us to know what's happening, what the speed is at 1.5. Was that correct? What the speed is? Okay. So the mass of the object was what? 25 pounds divided by the 32.2, and we want the speed at 1.5 seconds, and we subtract off the momentum the system had initially, which was 0. 25 over 32.2 times the velocity initial was 0. So here's the concept, and so the mathematics we want to carry out is integrating from 0 to 1.5 of our function 10 sine of 6t plus b minus 8.55 dt. Do you folks have any more markers back there, black markers anywhere? Okay. And so then this is going to be, and then so then this integrals, look what we can do since we zero out the initial momentum. We can just kick this factor, the reciprocal of this, over to the other side, and we'll have 32.2 divided by 25, and this result here should be our velocity at 1.5 seconds. At 1.5 seconds. Okay, so let's carry that out. 32.2 over 25, and we have to integrate this, be careful. So we're going to pick up a 10 times a negative cosine of 6t times what? 1/6. 1/6. Be careful with that. It's a classic place to make a mistake. Plus bt minus 8.55t. And then we're going to evaluate this from 0 to 1.5. And that should be our velocity at 1.5.
I think these are the right kind.
Okay, good. Thank you. Feel good? Any questions on the math so far? Okay, so if we put in 1.5 on this cosine function, let's make sure we're in radian measure, of course, on this. And let me go ahead and just do that myself. And you folks can punch along if you wish. Cosine of 9 radians. And if we put in the b of 5 right there at this point, marker's dead. Put in a b of 5 right there, and then we're going to have 5 times 1.5, which will be 7.5. Minus 8.55. Okay, and at the lower bound, does it zero out? No, because of cosine. Always watch out. People do that all the time in calculus. 0 on a cosine does not zero out. So that's going to turn this term positive because of the negative on the lower bound, and that becomes then a 1, and so you have to add then 10/6 times this factor, don't you, on the lower bound? I got negative 6.83. Anybody else get a result? And is there an answer to this thing?
Negative 4.
I got a wrong answer.
-2.7.
Oh, you did? Okay, good. I must have mispunched. So that is the answer they show in the book, negative 2.76. And you punched it, Julie? Okay, good. So I believe what we have here is correct then. At 1.5, we have a negative, what'd you say?
2.76.
Thank you. 2.76. And the units on this are
feet per
feet per second. Okay.
Noting that that's a vector.
Excuse me?
Noting that that's still a vector.
Yeah, and this means down the ramp, doesn't it? Down the ramp. Okay. Because the negative, everything we wrote was positive up the ramp. Okay, so what would happen to adjust this solution? That's the reason I carried the B through here. What would we have to do to adjust this and solve this thing to find the spot when it comes to rest again? Let's come back. Isn't that part B of the question? Okay. Let's come back to the drawings, all this work we did here with these drawings. See if they bring the camera over. There we go. Okay. So we want this thing to come to rest. Oh, actually, we were looking for a B, a choice of B that would cause this to come to rest after exactly one cycle. After exactly one cycle. Okay. Now, the loading that creates the impulse was indeed shifted down by 8.55. Right? By 8.55. This B, the way I drew this is I was thinking of this as being a value of 5. Okay. So what would have to happen for that we want this thing to go through one complete cycle? What value of B would we have to be carrying?
8.55.
We want that sinusoid to be lying right on that x-axis.
Yeah, because we want, well, hold it. Yeah, we want the effective sinusoid after one complete cycle to lie, here's our pi over 3 seconds. We want that impulse to be such that it makes it lie right on there. So that this area matches that area. So what's the answer they gave?
8.55.
Okay, and so what happens is we had to adjust this B value in such a way that we want this to be equal to 0, and so from this drawing, B minus 8.55, we want that to be forced to be here at the node, and so then B must be 8.55 pounds. It was a nice problem because it makes you think about the concept of the impulse visually as well as mathematically. You with me on that?
Yeah.
Okay, good. Okay, enough of linear impulse and momentum. We'll let you make sure you get onto that homework pretty soon, hopefully.